So that leaves us with the electrophilic aromatic substitution. Is that a possibility here? No. Why not? There's no aromaticity. So we can rule that one out as well. That means some new mechanism must be operating. Of course, you figured that out because that's why we're talking about this. All right, so what is the mechanism? What's going on? Start with the clues that we have. Br2 is red. Methyl cyclohexane is colorless. When we add light, only when we add light, or it turns out, or heat, either one of those. Heat will do this as well. But let's focus on the light, because that will actually help us figure out. So what's going on? Well, if light is a necessary aspect to get this reaction started, we know what reactant it's interacting with. Is it interacting with the colorless methyl cyclohexane, that visible light, or is it reacting with the red Br2? Why is Br2 red to begin with? What is it about it that makes that red, but this, for example, colorless? It's the way it's interacting with the light that's coming out of those light fixtures. This is colorless because it's retransmitting or passing the entire visible light spectrum. This, on the other hand, is absorbing a portion of the visible light spectrum, and what's left over we perceive as being red. All right, so this is what's interacting with those lights. So that's where we're going to start. So now we have to figure out what's going to happen here. So there's our bromine molecule. And we're going to shine that H nu on it, add that light energy photon. What happens to a molecule when you add visible light? Think back to 14C. We talked about the origin of color. Why are carrots orange? Because they absorb a portion of the visible light spectrum. But that energy has to go somewhere, right? This is absorbing photon. That energy has to go somewhere. Where does it go to? Electrons get promoted to higher energy orbitals. Now, in conjugation, we went from a pi to a pi star or something like that. We went from lower energy to high energy. So what's going on here? It turns out what we're doing here is taking an N electron, that's a non-bonding electron, so that's a lone pair electron, and putting it into the sigma star orbital. That's the only choices you have here. So what we're doing essentially is taking one of these lone pair electrons, putting it in the sigma star, and what that does is that weakens, because sigma star is against sigma, it's anti-bonding, it weakens the sigma bond, makes the sigma bond easier to break. It is if I took this piece of chalk and cut it halfway through with a file, it becomes easier to break. So what happens? Well, these things, the bromine-bromine bond is vibrating, of course. The bromine atoms move out and in and out and in. And when they go out and they're going to think about coming back in, they have a choice. They say, we can come back in because we're attracted to the bonding electrons, or we can keep going because we have lots of kinetic energy. Now, if you worked against, reduce the number of bonding electrons, so to speak, so you have half as many, now when the atoms move out, they go, we're just going to keep going. And so the bromine-bromine bond is broken. The two bromines move away from each other. But you have a choice of how you can break this bond. You can break it in a way that both electrons go to one atom. So that would make a bromine cation and a bromine anion. We call this heterolytic. Lysis for breaking, and the hetero meaning uneven. Or we can do it in a way where we give one electron to each bromine. Now, I'm using different curved arrows here than I've used before. Before we used the curved arrow that has two barbs on its head, and we're using that to indicate moving a pair of electrons. Here, I'm only moving one electron, so I have just one barb on the head of the electron, one fishhook, if you will. So this breaks it in a way that each bromine atom, we're now going to have two of the same thing, each bromine atom has one unpaired electron. Of course, the bromines have their lone pairs over here. We call this homolytic cleavage. Lysis, of course, breaking, and homo meaning even, the same. So we're breaking the electrons so each gets the same. Which do you think is preferred. If you're a bromine atom, would you rather have a positive charge, a negative charge, or be neutral? Neutral. Atoms like to be neutral. And this ends up being the favored process here. So this doesn't happen this way. It doesn't mean it can't happen in other processes. It just means here it doesn't. Now, the species that we've made has an unpaired electron. And things with unpaired electrons are called radicals. Also used to be called a free radical, but we dropped the free now, and so they're just radicals. So this thing, anytime you see something with one or more unpaired electrons, we call that a radical. This process is pretty easy to do. A bromine-bromine bond is pretty weak. It's on the order of about 46 kilocalories per mole of energy to rip this apart. That's about half as strong as your typical carbon-carbon or carbon-hydrogen bond. Those are in the 90 to 100 kilocalorie range. And I'm going to give you one more vocabulary word before we move along here. What we're doing, we're breaking in the presence of light. So we're going to call this process photolysis. There's the breaking and there's the light. And the whole idea of doing chemistry with light, called photochemistry, sounds kind of exotic, but in fact you're really familiar with it. Because if it didn't happen, then we wouldn't have hamburgers. We wouldn't have lettuce to put on hamburgers either. Right? What does, if you go outside here into the quad, what's doing photolysis? What's doing photochemistry? Plants. Right? Photosynthesis is photochemistry. They use light to build those new molecules. All right, so photochemistry is a pretty big area in chemistry. Now, we are at a point in our mechanism where we've made the bromine radical, often called Br dot. We don't have to draw the lone pairs in, just a single electron. So oftentimes we'll call that Br dot. Br dot. We want to figure out what happens next in the mechanism. Now, we haven't really talked about radicals, so it's kind of hard to look back on what we already know and say, this is what it's going to do. So we have to ask ourselves the same question we asked when we had carbocations. Its motivation is going to control its behavior. So what is its motivation? How does it behave? In other words, what are the radical fates? In exactly the same way we had carbocation fates. So let's go back to that radical. I'll just write R dot here. Doesn't really matter what the R is. It's the dot that's kind of important for this. If you're a radical, what's your issue, your anxiety? When you lie down on the therapist's couch and you're paying $300 an hour, let's suppose the bromine radical goes in to see its psychiatrist or its therapist, and its therapist says, so what's on your mind this week, bromine radical? And the bromine radical says, I have issues. What are the bromine radical's issues? By the way, it doesn't care about the economy, doesn't care about war, just those things don't matter. It's not those kind of issues. What issues does it have? Imagine you were a bromine radical. What would you like to have that you don't have? What do you have that you'd kind of like to get rid of? Electrons? Well, okay. Let's talk about electrons. Bromine radical has an open octet. So it has 7 electrons when it would really prefer 8. Remember that? Carbocations had the same issue. Now, it doesn't have a formal charge, but it does have another problem, and that is the unpaired electron. Electrons like to be in pairs if possible. So the way the radical behaves in a mechanism, regardless of where it comes from, is a function of trying to get rid of these things. Now, there are going to be 3 common things that radicals do, just like there's 3 common fates for a carbocation. And that doesn't mean there aren't other things that radicals can do, but these are the 3 most common. All right. Number 1, a good source of electrons to react with are pi electrons. They're just kind of sticking out there in space. So imagine we had, let's say, an alkene. And we have let's use bromine radical as an example for this. This bromine would like to fill its octet. It only needs 1 electron to do that. So what happens is we're going to use 1 electron from the bromine plus 1 electron from the alkene. Those are going to come together to form a new carbon-bromine bond. Now, the pi bond is 2 electrons, so we have to account for the other electron, and we're going to give that just to the other carbon. So that's going to give us a new radical. New carbon-bromine bond, a new radical. And why this radical is on, why we make the bromine here and put the radical there as opposed to put the bromine there and the radical there, we'll discuss later on. But this is a common kind of things to do, and so we'll call this addition to pi bond. Works with alkenes, works with alkynes, works with all sorts of radicals. And like many steps in radical mechanisms, this is driven by an increase in stability, by trading weaker bonds for stronger bonds. So essentially what we're doing here is trading the carbon-carbon pi bond for the carbon-bromine sigma bond. Remember that sigma bonds are generally stronger than pi bonds. So that's one possibility. Now we can do something else. I'm going to draw it with the same molecule here. Now, bromine needs electrons as well. Again, bromine radical. There's other sources of electrons within this molecule. There are the sigma bonds as well. So why not just steal an electron from the sigma bond, which is another possibility. So what I'm going to do is take one electron from the bromine plus one electron from that CH sigma bond, and the other electron then from the CH sigma bond becomes property of that carbon. So for all intents and purposes, what's happening here is the Br dot bangs into the propene and steals a hydrogen along with the one of the electrons. The atom just kind of comes along for the ride. It's the electrons it really needs. So the product of that is a new radical and a molecule of HBr. And this can happen with all sorts of different atoms being stolen, although hydrogens are by far the most common. And sometimes even you can steal whole groups of atoms, like methyl groups, but most of the time it's a theft of a single atom. So we're going to call this atom transfer. Transferring from this molecule to the HBr. Now the third radical fate that we're going to talk about is so obvious that most people don't even think about it. Let's come at this from think about this from like a role-playing point of view. Imagine that you are a radical. Everybody in here is a radical. And I don't mean, if this was UC Berkeley, it'd be easy, right? Everybody there is a radical. That's not the kind of radical I mean. I mean radicals with unpaired electrons. So you're a radical with an unpaired electron. The radical sitting next to you is an unpaired electron. Say hi to the radical sitting next to you. You both have a problem. You both have that same angst. It's like one of you is going into the therapist at the same time and the other one's coming out. You say, hey, how are you doing? What are you here for? Oh, well, I've got an open octet and an unpaired electron. Oh, so do I. You go, wait a minute. We can work together to solve our problem. How do two radicals work together to mutually solve their unpaired electron and open octet issue? They share. Because if each radical takes its unpaired electron and shares it with the other radical, then both things have full octets and no more unpaired electrons. So let's take a bromine radical and a bromine radical, right, on the way out from the therapist office. One bromine there, or excuse me, one electron there, one electron there. Each contributes one to the mutual bond, and we end up with a new covalent bond. Everybody's happy. We call this, or I call this, radical combination. So these are our three radical fates, and we're going to think about these exactly the same way we think about carbocation fates. Remember with carbocations, every time you see a carbocation in a reaction mechanism, same thing with radicals. Every time you see a radical in a reaction mechanism, regardless of where it comes from, think about resonance first. We're going to talk about resonance a little bit later today. But think about resonance and then think about the fates. Now, there's some parallels between radical fates and carbocation fates because in both cases, radicals and carbocations, those are species which are electron deficient. You may notice some parallels. For example, carbocations can also add two pi bonds. Pi bonds are nucleophiles. But the parallel is not perfect. There is one important differentiation between them, and that is radicals do not rearrange like carbocations do. Radicals do not rearrange. To be fair, there are radical rearrangements known, but they're really, really rare. So for our purposes, radicals simply don't rearrange. And you might say, well, why is that? A simple way to think about that is because radicals are missing one electron, but carbocations are missing two. Which is more desperate and therefore less fussy in the way it reacts? Radicals or carbocations? Carbocations, because they're short 2 electrons. Radicals are only short 1. All right, so now we're ready to go back to our mechanism. So let me just recap our story so far. So this is where we are, back to our mechanism. So far we have bromine in the presence of H nu or heat. Heat, by the way, works simply by adding more kinetic energy so that the bromines are vibrating with more vigor, and they have more kinetic energy, so when they get to the end of the bond, they have a greater chance of just moving apart. So that makes 2 bromine atoms, and now we have to figure out what's going to happen next. What are we going to do with methyl cyclohexane and our bromine radical? Let's see, what are our choices? We just talked about radical fates. Number 1, addition to a pi bond. Most of the time a carbon-carbon pi bond. What do you think? Applicable or not? No pi bond. What about atom transfer as a possibility? There's lots of atoms to transfer. What about radical combination? Is radical combination a possibility here? Well, it can happen. These 2 Br2s, these 2 Br dots, that I just made, can recombine and go back where they came from. So break apart, go back together. Break apart, go back together. It's like if you dump your significant other and turn your back and take 3 steps down the hallway and then turn back around and go, oh, I'm sorry. That's what's happening. And believe me, like this, it's usually not productive. Although I wouldn't know. I've been happily married for 11 years now. 10 years there. All right, anyways. So what we're left with is atom transfer. Does that look like it'll move the mechanism forward? Remember, we have to operate on this hydrogen. We have to take that hydrogen away. That's what atom transfer does. It takes atoms away. So let's operate on this hydrogen. I'm going to have the bromine take the hydrogen away along with 1 electron, plus the other electron from that CH bond becomes the property of the carbon. So we end up with a new radical, methyl cyclohexyl radical plus HBr. Now, this step should be intellectually satisfying for 2 reasons. Number 1, it makes one of our 2 products, HBr. Number 2, it begins to do the bond changing at the carbon where we need the bond changing to occur, next to the methyl group. But that's circular logic, because we said, I'm going to make the bond change here because that's what the product is, and therefore it's satisfying because the bond change occurs where the product is. So that's not a good reason. But it looks like it may get us to where we need to go. So let's see if this is truly the best choice. Now, when we do this atom transfer, this bromine could take this hydrogen or a methyl hydrogen or any one of these methylene hydrogens. It could steal the entire methyl group. Why this particular hydrogen? Let me ask a broader question. In general, when you have 2 things, A and B, reacting to make something C or D, we pick pathway C over pathway D because C... If you can do electrophilic addition to an alkene, let's say you're adding HBr to an alkene, and you can make a primary or secondary carbocation by adding the HBr, do you make the primary or the secondary carbocation? Secondary, because the secondary compared to the primary is more stable. So that's the fundamental idea we've used. In other words, the argument is this hydrogen is probably being taken away because this radical product is more stable, lower energy of activation for this pathway. Is that true? Well, to find out if that's true, we need to explore a little bit about radical stability. I know that sounds kind of like an oxymoron, radicals being stable, right? Like political science, that's an oxymoron. Right? Okay, thank you. All right. So let's talk about radical stability. Now, radicals carbon radicals are electron-deficient species just like carbocations. Carbocations have an open octet and 6 electrons. Radicals have an open octet and 7 electrons. But in both cases, it's electron deficiency on carbon. So what we can do is take the kinds of features we talked about when it came to carbocation stability and see if they apply to radicals, because after all, they're both electron-deficient carbons. So when we talked about carbocations, one of the things we talked about was the number of substituents. So in a carbocation case, we would say methyl carbocation compared to a primary, I'll just put an R group there. A primary carbocation, which is more stable, methyl or primary? Primary, because the R group is electron donating, it helps satisfy some of the positive charge. And by extension, 2 R groups, and then all the way up to 3 R groups. In other words, methyl carbocation, the least stable, followed by primary, secondary, tertiary. When we talked about carbocations, we were free to use secondary and tertiary all we want. Primary, you better have a good reason, but they're allowed. Methyl, on the other hand, so unhappy that we never ever invoke a methyl, at least not just to CH3. We have methyl with resonance, but methyl by itself, no good. Now, what about radicals? Let's compare same radical. CH3, methyl radical, a primary radical. We call this primary radical for exactly the same reason we call this a primary carbocation. The carbon that bears the unpaired electron is directly attached to one other carbon. Then we have a secondary radical and a tertiary radical. Well, what do we think about the stability here? Should methyl be more or less stable than primary? The carbon that bears the unpaired electron is electron deficient. An alkyl group is electron donating. So should a methyl radical be less stable or more stable than a primary radical? Less stable, for exactly the same reason as a carbocation. And the same trend follows. Tertiary radicals happiest, secondary radicals okay, primary okay, methyl radical. Well, it turns out that methyl radicals, we were forbidden to use methyl carbocations, but methyl radicals, turns out, are okay. And that's probably the issue of being not quite as desperate as a carbocation, because it's only short 1 electron instead of 2. So we are allowed to invoke CH3 radical, CH3 dot, but we're not allowed to invoke CH3 plus. So this is degree of substituents. What else did we talk about when it came to stabilizing carbocations? Yeah, resonance. It wouldn't be a day in 14D without talking about resonance. So how does resonance work for carbocations? Let's see, here is a resonance carbocation case. Put some lone pairs. Lone pairs on the atom next door to the open octet, so remember we can combine those to make, I'll let you draw that while I'm erasing. When we combine those in our resonance, other resonance contributor, we get this guy. Lone pair became the pi bond. Carbon's octet gets filled. Oxygen's octet is still filled, but it has the positive charge. Now, in this particular case, this is actually the oxonium-ion structure again. Oxonium-ion because it has oxygen with 3 bonds and a positive charge. And in this case, the oxonium-ion structure is happier, a more significant resonance contributor than the carbocation structure, because in the oxonium-ion, all atoms have full octets. Number 1 most important rule about evaluating resonance contributors. All right. And we can do this with nitrogens and halogens and so forth. What about in a radical case? So I'm going to try having an oxygen next door to the radical. All right. So the carbon has an open octet. It's got those 7 electrons. So let's bring these guys over, just like we did for the carbocation. let's see, we have a dot there, we have a lone pair there, and a positive charge there. Still an oxonium ion. What do we think about that new structure? Does every atom have a full octet? Yes. And then some. There's a problem with this. Who wants to criticize? Carbon has too many electrons. 2, 4, 6, 8. I'm counting the 4 for the CH bonds, plus this guy. 9 electrons. Can carbon have 9 electrons? Never, ever, never, ever, never, ever, ever. No. So that's no good. All right, so the problem here is the reason carbon has 9 electrons is because it is 7 to begin with, and we're importing a pair. Let's suppose we only import 1. So instead of bringing over both electrons, let's try this. So I'm only going to use 1 electron, plus 1 electron. Still going to get a pi bond. And that's my new structure. What do we think about that one? Does everybody have a full octet? Uh-huh. And then some. What's the problem here? 1, 2, 3, 4, 5. Excuse me, 1, 2, 3, 4, 5, 6. What am I missing? 2, 4. That's what I'm not doing. Dr. Bacher suggested I bring coffee, and I only brought water today. Let that be a lesson. Dr. Bacher is very wise in that way. I need coffee. 2, 4, 6 in the OH bond, 8 in the lone pair, plus 1 more makes 9. Can oxygen ever have 9 electrons? No. No good. Now you can play this game with other elements with lone pairs and moving the electrons around in different ways, but you discover that I cannot use a lone pair adjacent to a radical to provide resonance stabilization. This is another way in which carbocations and radicals are different. Carbocations love lone pairs next door. Radicals does not help with stability at all. All right, so now we've talked about number of substituents. We've talked about resonance. Let's go back and analyze this case again. And why is it that particular hydrogen gets removed? So we said this is what we did. Why should we do that instead of, let's say, taking away a hydrogen from the methyl group? It's the same thing. Use the electron from the bromine, 1 electron from the CH bond, give the other electron of the CH bond to the carbon, CH2, and that would put the unpaired electron right there. Which one of these 2 pathways do I pick? First one or second one? Which one of these 2 pathways, first one or second one, leads to the more stable radical? First one or second one? Tertiary radical. The carbon that bears the radical is directly attached to 3 other carbons. This radical is this radical methyl primary, secondary, or tertiary? It's primary. And which is more favorable? Tertiary. Matter of fact, this is the only hydrogen in the molecule whose removal leads to a tertiary radical. This is the CH3 hydrogens are primary radicals. These guys are all our secondary radicals. So the reason the hydrogen next to the methyl group gets abstracted, gets removed, is because it's the most favorable abstraction. So that makes sense in terms of our moving our mechanism forward. All right, so now we have, just to recap where we were again, we had, because I know your mechanism tends to get a little scattered as you go through this. So that becomes 2 bromine radicals. The bromine radical, we said, takes away what some students have called the armpit hydrogen. See, there's the arm, and that's the armpit. That's not a technical name, by the way. And so that makes this tertiary radical. And now we need to come up with the next step in the mechanism. And our next step in the mechanism is to get this guy to become the product. We can do it in one step. All right, how are we going to do that? So we want to take that radical and convert it into that bromine. There are 3 sources of bromine within the reaction. So there are 3 ways to do this. So let's evaluate. I'm going to write them out in generic form, well, kind of skeleton form here first, and then we'll flesh out the details as we figure them out. So 3 versions of the incomplete step. All right, so what is in the mechanism at this point that can supply that bromine atom that we need? Who's got an idea? I'm sorry? The other bromine. Do you mean, well, when we say bromine now, do you mean bromine atom? That's a Br dot in this case, right? If you look at the periodic table, bromine with 7 electrons is elemental bromine atom. Or do you mean Br2 bromine? Molecular bromine or bromine atom? Or both. We're looking for sources of bromine, right? So I could use a Br dot and simply do a radical combination. Or I could use Br2 and do an atom transfer where the radical steals one bromine atom from the Br2. So that would generate a Br dot over here. One more source of bromine. Source of bromine that's floating around in the reaction. Not Br2, not Br dot. How about HBr, the stuff I made in the second mechanism step? So maybe I could do an atom transfer where I steal a bromine from HBr. So that would make the new carbon-bromine bond, and it would make an H dot. Now, mechanistically, these are kind of 2 different categories. We have, or in terms of radical fates, these are 2 categories. This is a radical combination. This is an atom transfer. Which one do you think we should pick? Which one is energetically, thermodynamically more favorable? 2 radicals come together to make no radicals. 1 radical reacts with a molecule to make another radical, or 1 radical reacts with a molecule to make another radical. Should I pick 1, 2, or 3? I like 1 because we're forming a new bond. We're not paying a price for it. But I'm here to tell you it doesn't happen that way. That's because there's something I didn't tell you. There's a fact that didn't really matter up to this point that I'm now going to tell you, and we're going to rationalize why this doesn't really happen. The fact is this. Of all these radical mechanism steps we've talked about, here's a good example, here or here. While they have a certain delta G associated with them because we're changing the bonds, it turns out the energy of activation for radical steps tends to be very low. So typically, overall, energy of activation for radical steps is small. And what happens to rate when energy of activation is small? Very fast. So in other words, these radical processes, individual mechanism steps, once you get things started, individual mechanism steps move along at a good clip. And what that means is you don't have an opportunity for the concentration of an intermediate to build up. So as soon as I make methyl cyclohexyl radical, it immediately reacts. Here's a metaphor. Let's see if this works. When I feed the cats in the morning, there's much meowing and gnashing of teeth and rubbing and getting up on hind paws and being cute because they want to be fed. It takes a little while to open the can, especially because if I'm doing it at 5:30 in the morning, I'm not exactly awake. I got to find the can, I get it the little tabby out and pull it open and then get a spoon and find a clean plate and put it all. It takes a little while to get it started. But once it gets started and that food goes down on the plate, it's gone. My cats have a very low energy of activation when it comes to eating. In other words, the food doesn't hang around very long. So if they're in the middle of eating, if they're sucking up that can and I go and get another can because I'm feeling particularly generous and because they've whined me and meowed loudly that they want more food. By the way, this doesn't happen. They do meow, but they don't get a second can of food. But let's just suppose I'm in the process of putting out a second can of food. That first can of food is gone. The food, the food plate just is not allowed to get a lot of food on it because once it's out there, the energy of activation for eating food is very low. It goes away quickly. So radicals are the same way. Once a radical is produced, it reacts quickly. And the concentration of any given radical in the reaction mechanism tends to be low. Now, what does that mean? It means here I'm asking for two things which are present in low concentration to find each other. The chances of that happening are pretty small. Let me use a different metaphor. If we think of two radicals coming together as a collision on the freeway, those certainly happen in California, do they not? But let us suppose we think about the collision of two things which are relatively uncommon. This is a green 1964 VW. This is a red 1967 Mustang, something we definitely don't want to bang into, but nonetheless, right? What's the chance of two cars, any two cars, finding each other on the freeway on any given day? Pretty high, especially if it's the 405 on a Friday and you have to drive north. That's going to happen right there, you know it. But the possibility of that green 1967 or whatever year it was Volkswagen Beetle finding the red Mustang, also a vintage car, these two finding each other, there aren't that many green Volkswagen Beetles and there aren't that many vintage Mustangs in Southern California anymore. So the chances of them finding each other is low. Same thing here. Two things present in low concentration, two radicals, their chances of finding each other low. So while this is thermodynamically quite nice, kinetically doesn't happen. So this rare to say the least. We're not going to consider that to be our last step for the mechanism. For these other two, now we have a choice between, in both cases, we're making a new carbon-bromine bond. The difference is we're breaking a Br2 bond versus we're breaking an HBr bond. And it turns out a Br2 bond, as we said before, has an energy of about 46 kilocalories per mole. I don't recall the exact number for HBr, but it's somewhere up around 80. So it costs almost twice as much energy to rip apart an HBr bond as it does to be a Br2 bond. So if you're a methyl cyclohexyl radical and you want to steal a bromine, who do you steal it from? Br2, because it's easier. If you're going to go rob someone, do you rob the guy that's asleep or do you rob the guy that's sitting on his front porch with a shotgun out? Right? I know that's not a PC metaphor, but this is easier. So this is what you do. This is our last step in the mechanism. However, and here's your thought for the day. Perfect timing. This creates a problem. We have an unresolved issue in this mechanism step. So your job for next time, what's that issue? What's the consequence of it? That's what we're going to pick up next time.